Hello, my name is Anthony Troxell, and today I'm going to be talking about wide bandgap semiconductors and their use in power electronics. When we look at our outline, we're going to start with an introduction, jump into what are wide bandgap semiconductors, then look at some power electronics, and then we're going to take the wide bandgaps and see how we can make them useful in power electronics. This will be followed by the conclusion. First up is the introduction. The power electronics market today is roughly a $40 billion industry, but this market is expected to grow into a $50 billion industry by 2025. If we look at gallium nitride and silicon carbide, they both accounted for about 1% of the market in 2018. But by 2025, they're expected to be roughly 6% of the market share. And if we look at their growth, they're expected to grow by about 30% in this market year over year over that time span. Two good examples of where wide bandgap semiconductors can really help with systems of today are with photovoltaic systems, where we could see lower cost, smaller size, longer lasting inverters that can actually handle higher voltages. And another place is with electric vehicles, where we can see faster charging, lower power losses, increased power density, and an overall lower system cost. But what about an extraterrestrial example, like Venus? The environment there is extremely harsh. With high temperatures and a dense corrosive atmosphere, today's silicon-based systems wouldn't even last a day. And in fact, the only time we've sent a probe to Venus, it lasted just a little over 2 hours. But with wide bandgap semiconductors, there's some promise here. Wide bandgap semiconductors can operate at higher temperatures and are able to survive higher levels of radiation. But they also have improved efficiency in power switching and RF applications, which could potentially improve communications. Next up is, what are wide bandgap semiconductors? So first, we need to define what is a wide bandgap semiconductor. And so here we're going to define any semiconductor with a bandgap energy greater than 2 electron volts as a wide bandgap semiconductor. Now, in the plot on the left, we have two areas of interest. At the bottom of the plot, I've highlighted an area which contains silicon, germanium, and gallium arsenide. And so these are all narrow bandgap semiconductors that have a wide range of uses today. And on the left side, we have silicon carbide, gallium nitride, and diamond, which are all wide bandgap semiconductors that have potential uses for power electronics now and in the future. So here we take a little bit closer look at where those band gaps lie for those examples, with silicon carbide having a band gap of 3.26 electron volts, gallium nitride having a band gap of 3.39 electron volts, and diamond having a band gap of somewhere between 5 and 6 electron volts. So these all fit our definition of wide band gap semiconductor. Let's learn a little bit about power electronics. So let's talk about some applications. Would you like to have more energy efficient appliances, potentially lower your electricity bills? How about battery chargers that can charge faster and more efficiently for your phone? Or a computer power supply that's more energy efficient and supplies cleaner power? We already talked about electric vehicles and solar inverters and how those can improve. What about RF amplifiers for cellular communications? Or uninterrupted power supplies that are more energy efficient and may last longer? Maybe they're a little bit smaller. Or vending machines, we can make those more energy efficient, and maybe those savings get passed on to you as the consumer. The applications don't just stop there. Power electronics have a wide range of uses in places like power transmission and transportation, into areas where robotics and assembly lines are involved, or maybe even heavy machinery. They could also be found in data centers or industrial applications with cooling. And as we could see, silicon carbide and gallium nitride, both wide bandgap semiconductors, have the potential to replace silicon in many of these applications. So let's take a little bit of a deeper dive into where the power electronics are found in each one of these applications. So we're going to start with a diode rectifier, which converts AC voltage into a fixed DC voltage. And the main components of this are, of course, the power diodes that are found in the circuit, which I've highlighted. Uh, Next up would be that of static switches. So the static bypass switch that's highlighted could be used for things like the uninterrupted power supply. And this block diagram shows exactly how that's done. Another category of converters is that of the controlled converter. And the first example of a controlled converter is a DC to DC converter called a chopper. So in figure 6, I've shown an integrated gate bipolar transistor that's being used in a chopper. And here we're taking one DC power supply and we're turning it into another DC power supply by way of averaging. So we're going to turn on and off this transistor and then average the voltage across the load later on. The next example of a controlled converter is a DC to AC converter or inverter. And here we're using power MOSFETs in an H-bridge configuration to take a DC supply and turn it into an AC supply, which is depicted on the right. The next example of a controlled converter is that of the AC to DC converter or controlled rectifier. And here we're taking thyristors, which can be thought of as SCRs or controlled diodes, and we're using those to pick which part of the sine wave we actually want to hold on to and use to convert into a DC voltage. And the final example of a controlled converter is that of the AC to AC converter, which uses what you can see as a triac, which is basically taking two of those thyristors and merging them into one special case device called the triac. And now we can take an AC voltage and control how much of that AC waveform we actually want to use to convert into another AC voltage. And that covers controlled converters. It's time to see what makes wide bandgap so useful in power electronics. So let's take a second to compare silicon to some of these wide bandgap semiconductors. So the first thing that we'll notice is the band gap. In silicon, this is 1.12 electron volts at room temperature, but in silicon carbide and gallium nitride, we're roughly 3 times higher than that. And this means that it takes more energy to excite electrons from the valence band into the conduction band. Another thing that we'll notice is down at the bottom of the chart is the breakdown field. So this is the critical electric field. Now for silicon, this is about 3e5 volts per centimeter. But for the wide bandgap materials, we can see that we're roughly an order of magnitude higher. And this is a key parameter in determining the breakdown voltage in devices. One final thing to touch on from this chart is the thermal conductivity. For silicon carbide, we can see that it's almost 2.5 times larger than that of silicon, which means that silicon carbide is much better at dissipating heat, and so the cooling requirements for silicon carbide are then significantly lower. We're going to take a moment to look at that breakdown voltage we talked about, because the most unique feature of a power semiconductor device is its ability to withstand high voltages. And this can range anywhere from 20 volts to 5,000 volts, depending on the application. In figure 11, we see a depiction of doping concentration versus breakdown voltage. When comparing silicon to silicon carbide, we can see that it takes roughly 2 orders of magnitude less doping concentration on the lighter dope side of the junction for silicon to reach the same breakdown voltage as silicon carbide. And now, this lower doping concentration is going to prove critical when we look at things like temperature and for depletion widths and on resistances later on. When we're talking about power electronics, sometimes we're talking about environments that are harsh and with high temperatures, like an engine block or a reactor, or maybe even the planet Venus. And an important thing to talk about when we talk about temperature is the intrinsic carrier concentration of the semiconductor. So for silicon, the intrinsic carrier concentration is about 1e10 at room temperature and goes up to about 1e15 at 540 degrees K. So what this means is, let's say I have a PN junction with doping concentration of 1e13 on the lighter dope side. It means I cannot turn off that device above about 410 degrees Kelvin. And even in the example of 1e15, that means I cannot turn my device off above 540 degrees K. It's not possible. The intrinsic carrier concentration is too high. But when we look at silicon carbide, this value only reaches 3.9 E7 even at 700 K. So that means I can operate well above that range and still know that my devices will turn on and off appropriately. So earlier when we were talking about the breakdown voltage, I mentioned the importance of doping concentration with relation to the depletion width. So I thought it would be a good idea to give an example of the improvements going from silicon to silicon carbide with respect to breakdown voltage and depletion width. So at the bottom of the page, I provided the formula for depletion width for a one-sided junction, because that's what we're going to be looking at here is a PN junction. And the example that I have is for 1000 volt breakdown voltage for both materials. So for silicon, to achieve 1 kV, we're going to need about 1.5 E14 for the doping concentration on the lighter side of the junction. And for silicon carbide, this raises to about 4 E16 to achieve the same breakdown voltage. And when we plug these values in to the formula for depletion width, we can see that this results in about a 10 times smaller device, and that the device will have a much lower on resistance due to the higher doping concentration. And this is all while achieving the same breakdown voltage. But as we just saw, what about how this affects the temperature range that these devices can function over? With the much higher doping concentration for silicon carbide, we can see that we can use this over a wider range of temperatures as well. That brings us to our conclusion. So over the course of this presentation, we've seen that wide bandgap semiconductors are those with a bandgap greater than 2 electron volts, that the wide bandgap semiconductors of silicon carbide and gallium nitride are emerging materials that have promising futures in power electronics, that wide bandgap semiconductors have a wide range of uses in power electronics, both terrestrial and extraterrestrial, and wide bandgap semiconductors that are used in power electronics can allow us to work at higher temperatures. They can handle stronger electric fields, which lead to higher breakdown voltages. We can reduce the size of the devices, and they can have lower on resistances, which are all great things to have for power electronics. And with that, I provide you some references and bid you a good day.